Hello my friends and welcome back to the You Can Do TV channel. In the vast open-pit mines of Chinco, Peru, giant machines dominate the landscape, true titans of modern mining. One of the most iconic is the Caterpillar 797F mining truck, a behemoth designed to carry up to 400 tons of material per load. With its massive 4,000 horsepower engine and rugged construction, the 797F operates in some of the toughest conditions, navigating the mountainous terrain with surprising agility and unmatched durability. Working alongside the 797F is the CAT 7495 electric rope shovel, often referred to as the giant shovel. This massive piece of equipment can lift more than 100 tons of material in a single pass, efficiently loading the mining trucks in just a few cycles. Its powerful electric motors and precision control allow it to move vast amounts of earth with extreme accuracy. Together, these machines form the backbone of Chinalco's copper production operations, ensuring continuous, high-volume extraction. Every component, from hydraulic systems to onboard technology, is engineered for reliability, performance, and safety. In a place where downtime is costly, these machines are built to work relentlessly, keeping the heart of Peruvian mining beating strong. At Schmiedewerke Groditz GmbH, high-performance forged products are manufactured to meet the demanding needs of the mechanical and plant engineering industries. Steel production begins in a modern electric arc furnace using 100% sorted scrap to melt up to 50 tons per batch. After smelting, ladle furnace treatment and degassing in VD/VOD units ensure optimal purity and composition. The molten steel is cast into ingots tailored to forging requirements, up to 76 tons. For critical applications, electroslag remelting, ESR, is used to enhance homogeneity. Forging begins after heating ingots to 1,200 degrees Celsius, using a powerful 60 meganewtons press and precise manipulators. Components such as turbine shafts or wheels are shaped through pre-forging, upsetting, and final forming. Smaller forgings, up to 20 tons, are processed on a 27 meganewtons press. All forgings undergo rigorous heat treatment in calibrated furnaces, with quenching in controlled oil or water tanks. For large components up to 8.5 meters, vertical heat treatment ensures perfect concentricity. Finished parts are then tested via ultrasonic, tensile, impact, and structural analysis. After final inspection, preservation, and marking, products are cleared for global dispatch, ensuring world-class forging precision. The process begins with large steel slabs being heated in a furnace at temperatures above 1,200 degrees Celsius. Once red hot, the slabs are fed into a powerful 5,600 millimeters rolling mill. Giant rollers exert enormous pressure, transforming the slabs into super-wide sheets in a single pass. Precision sensors and automated controls ensure perfect thickness, flatness, and surface finish. After rolling, the steel is smoothed, cooled by high-speed water, and then passed through edge cutting and marking stations. Finally, the finished slabs are sent to storage or prepared for shipping. This mill offers unparalleled capacity, productivity, and quality in the production of heavy steel plates. The fully automatic hot forging nut machine line is a high-efficiency system designed for mass production of nuts through hot pressing. This integrated equipment line includes several critical stages: heating, shearing, forging, and forming. Raw steel bars are first heated in an induction furnace to a precise forging temperature, typically between 1000 degrees Celsius and 1200 degrees Celsius. The red-hot billets are then cut to length by a high-speed shear unit. Once cut, the billets are automatically transferred to the forging press. Here, a series of precision dies shape the material into the desired nut geometry. Multi-station forging presses enable the formation of complex shapes in a single cycle, improving consistency and production rate. After forming, the hot nuts are transferred to a trimming station where flash and excess material are removed. The entire process is synchronized and PLC controlled, ensuring minimal human intervention and high repeatability. The system includes automated feeding, temperature control, lubrication, and ejection functions. The finished nuts are then either air-cooled or sent to a quenching station, depending on material requirements. This fully automatic line is ideal for producing hex nuts, flange nuts, and other industrial fasteners with high precision, strength, and production efficiency, making it essential for modern bolt and nut manufacturing. Feeding the 75 tandem mill requires precise coordination and continuous material input. Steel strip is uncoiled and guided into the mill, where multiple stands progressively reduce thickness. Consistent tension, alignment, and speed control are critical to ensure uniformity and surface quality throughout the rolling process, maximizing efficiency and minimizing material defects. In rural areas, traditional aluminum pot casting is still practiced using time-honored methods. The process begins by melting scrap aluminum in a clay furnace fueled. Once liquefied, the molten aluminum is carefully poured into sand molds shaped like pots. Craftsmen often use hand tools to ensure the shape and thickness are correct. After cooling, the molds are broken to reveal the rough pots, which are then polished and trimmed. Despite the simple tools and setup, the skill involved is remarkable. These handmade aluminum pots are durable, affordable, and widely used in everyday rural cooking across many parts of the world. The sand casting process is widely used for producing heavy-duty metal components. It begins with the creation of a pattern, a replica of the final product. This pattern is placed inside a molding box or flask, where treated sand is tightly packed around it. After painting the mold to improve surface finish and durability, the pattern is carefully removed, leaving behind an accurate mold cavity. Next, a gating system is installed, consisting of pouring cups, sprues, and gates, which guide the molten metal into the mold. The mold is divided into two sections, the cope, top, and the drag, bottom. For large castings, the mold is built in multiple parts. Once the sand sets, the pattern is removed, and the mold halves are reassembled to form the cavity. Molten metal, prepared in a furnace with strict control of temperature and composition, is then poured into the mold. The risers ensure a constant metal supply as the part cools, minimizing shrinkage voids. After solidification, the mold is broken during the shakeout process, and the sand is reclaimed and reused. The raw casting includes excess metal, risers, gates, and feeders, which are removed using a casting degating hammer from Suzhou Weijing Automation Company, Limited. Unlike manual hammers or flame cutting, this tool is faster, safer, and prevents damage to the casting surface. Additionally, investment casting offers higher precision for complex parts. This method uses a ceramic mold that is destroyed during the process, making it ideal for fine, near-net-shaped components without expensive tooling or long lead times. The HUB forging line is a high-performance industrial system designed for the efficient and precise production of forged components, particularly in the automotive and heavy machinery sectors. This advanced line integrates several stages, including billet heating, descaling, preforming, final forging, and trimming. Using state-of-the-art induction heaters, billets are rapidly brought to optimal forging temperatures. Automated descaling ensures clean surfaces for quality finishes. High-tonnage forging presses then shape the metal with exceptional accuracy, while robotic arms handle positioning and transfer between stations. The HUB forging line is capable of producing high-strength parts like hubs, axles, and wheel components, with excellent dimensional stability and mechanical properties. Its energy-efficient design reduces waste and downtime while enhancing safety and productivity. Integrated sensors and digital control systems monitor every step, ensuring consistent quality and enabling predictive maintenance. Whether for high-volume output or customized batch production, the HUB forging line sets a benchmark for modern metal forming technology, delivering strength, precision, and reliability with every forged part. Aluminium is an extremely pliable and adaptable metal. Most of the aluminium that you will have come across in your own life will have been rolled or extruded, the two main types of finished aluminium products. Aluminium extrusion is the act of forcing heated aluminium logs, or billets, through a precast steel die. This action squeezes the heated aluminium into a predetermined shape, thus creating an aluminium extrusion. The aluminium extrusion process begins with casting aluminium alloy logs. These logs are produced by melting high-purity aluminium, recycled scrap, and alloying elements like magnesium and silicon. During casting, unwanted gases are removed and the metal is filtered for purity. Logs, typically 20 to 30 feet long, are cooled, homogenized to improve microstructure, and cut into billets. Billets are then heated to 800 to 1000 degrees Fahrenheit to make them malleable, while extrusion dies are also heated to avoid thermal shock. A billet is loaded into the extrusion press, and under high pressure, up to 100,000 psi, it is forced through a steel die, forming the desired cross-section. This is known as direct extrusion. Alternatively, in indirect extrusion, the die moves over a stationary billet, which reduces friction and results in better dimensional control. As the extruded aluminium emerges, still extremely hot, it is rapidly quenched using fans or water spray. Quenching locks in the alloy's microstructure, improving mechanical properties. However, quenching can cause distortion, so the extrusion is stretched to straighten and relieve internal stress. Next, the extruded profile is cut to required lengths, measured, and inspected using calipers or coordinate measuring machines to ensure tolerance compliance. Profiles are then aged in ovens at elevated temperatures for 6 to 8 hours to reach full hardness, e.g., T6 temper. This age-hardening process ensures the material achieves its final strength. After aging, extrusions may undergo additional fabrication such as CNC machining, punching, drilling, or welding, e.g., fusion or friction stir welding. They can also be anodized or painted for finishing. Their ability to control every stage, from alloying and casting to die design and finishing, ensures high-quality, sustainable, and lightweight aluminium solutions. SAPA's expertise in both direct and indirect extrusion supports a wide range of industries, including automotive, renewable energy, construction, and aerospace. Through innovation and vertical integration, SAPA Extrusions continues to deliver advanced aluminium solutions that are strong, recyclable, and globally transformative. Installation of ultra-large machinery at the FAMOT factory. This complex process involves precision positioning, heavy-duty lifting equipment, and careful alignment of structural and mechanical components. Specialized teams coordinate to ensure safety and accuracy during the setup of these massive industrial systems, critical for advanced manufacturing operations. Ginuti Carrillo's hot forging process is a precision-driven operation designed for high strength and reliability. It begins with cutting steel or aluminum billets to specific lengths. These billets are then heated in a furnace to temperatures between 1,100 degrees Celsius and 1,250 degrees Celsius, making the metal malleable for forging. Once heated, the billets are transferred to forging presses, mechanical or hydraulic, where they are shaped inside closed dies. This operation aligns the metal's grain structure with the part's geometry, significantly increasing mechanical strength. After forging, excess material or flash is removed using trimming presses. In some cases, a calibration step follows to improve dimensional accuracy and surface finish. The parts are then cooled in a controlled manner, or sent for immediate heat treatment to enhance hardness and durability. The final steps include quality inspection using dimensional and structural tests to ensure every component meets strict standards. Some parts may go through additional machining depending on end use. Ginuti Carrillo's hot forging line ensures consistency, strength, and performance in each forged piece, serving critical sectors such as automotive, hydraulic, and industrial machinery. The Boeing 737 MAX assembly process is an extraordinary showcase of precision engineering, cutting-edge manufacturing, and global coordination. This is how one of the world's most advanced commercial aircraft is put together in record time. It begins with major fuselage sections, forward, mid, and aft, arriving at Boeing's Renton, Washington facility from partner manufacturers across the globe. These sections are pre-outfitted with wiring, ducting, and basic systems, reducing time on the final assembly line. Automated guided vehicles, AGVs, and overhead cranes carefully move and align each fuselage segment into massive joining fixtures, where hundreds of rivets and bolts secure them into one seamless body. Simultaneously, the wing components, crafted for maximum lift and fuel efficiency, are brought in and attached to the fuselage. Precision is crucial as technicians align the wing box to the center fuselage and install critical control systems, fuel lines, and structural reinforcements. The vertical fin and horizontal stabilizers are then fitted to the tail section, completing the airframe structure. One of the most defining moments in the assembly is the installation of the LEAP-1B engines. These ultra-efficient, high-bypass turbofan engines are mounted under each wing using advanced pylon systems and undergo thorough inspections. Meanwhile, inside the fuselage, cabin crews install insulation, sidewall panels, flooring, electrical systems, and avionics. The flight deck is outfitted with advanced navigation and control systems, forming the aircraft's digital brain. After full structural and systems assembly, the plane moves into the paint hangar, where it receives its customer-specific livery. Once painted, it undergoes a battery of ground checks, testing everything from landing gear deployment to hydraulic systems and electrical continuity. Engine run-ups and taxi trials follow on the tarmac. The final phase is the flight test, where Boeing test pilots take the aircraft through various maneuvers, engine power settings, and safety protocols to ensure performance matches specifications. Once the aircraft passes all checks, it's officially certified and delivered to the customer. This entire process, from fuselage join to final delivery, can take just over 10 days, thanks to Boeing's lean production methods. The result is a state-of-the-art jetliner, built for safety, efficiency, and long-haul performance, ready to take to the skies. Weir American Hydro focuses on precision engineering and technical excellence in the design and manufacture of hydroelectric equipment. Their core expertise lies in advanced computational fluid dynamics, CFD analysis, finite element modeling, FEM, and 3D CAD design, allowing for high-efficiency turbine and component optimization. The company specializes in Kaplan, Francis, and Pelton turbine technologies, offering full refurbishment and new unit capabilities. Their in-house machining and welding facilities ensure tight tolerances and superior metallurgical integrity. Hydraulic performance testing and model validation are conducted to ensure optimal flow characteristics and cavitation resistance. From spiral case redesign to wicket gate upgrades, every component is engineered for durability, efficiency, and ease of maintenance. The new CAT 320 GC, 320 and 323 excavators are built on a unified platform to streamline manufacturing and improve parts availability. All models come pre-equipped with essential sensors and cameras, offering full technological integration. The standardized design simplifies updates, allowing easier adaptation to future advancements. This modular platform is the same globally, ensuring consistent quality and faster service. With features like remote flash updates and smart system integration, these excavators enable real-time performance improvements. Designed for speed, flexibility, and uptime, they meet modern customer demands while setting a new benchmark in construction equipment innovation. Whole-set turbochargers, manufactured by Cummins Turbo Technologies, are precision-engineered for performance and durability. The process begins with casting the turbine housing from high-temperature alloys. The compressor wheels are CNC machined from aluminum or titanium. Shafts are precision ground and dynamically balanced. The assembly includes fitting the turbine and compressor wheels to the shaft, installing journal and thrust bearings, and sealing systems. After full assembly, each unit undergoes rigorous testing for pressure, balance, and durability. Whole-set turbos often include advanced features like variable geometry and electronic actuators, ensuring optimal performance in demanding diesel engine applications. Colosio SRL is a global leader in manufacturing high-performance die casting machines. Their product range includes cold chamber machines with locking forces from 140 to 3,200 tons, featuring motorized hoods, tie bar withdrawal systems, and the COL block automatic die locking system. Hot chamber machines range from 30 to 320 tons, equipped with electric doors, chromed tie bars, and real-time injection position reading. Colosio emphasizes precision with hydraulic auto-leveling slides, fluid collection tanks, and forged steel plates. Their fully integrated production includes in-house engineering, component machining, and assembly. Proprietary software, closed-loop injection control, and teleservice ensure reliability and remote monitoring. Voith Hydro in York, Pennsylvania is North America's premier hydropower manufacturing facility. It features a hydraulic test lab and cutting-edge CNC machining for precision turbine production. Engineers design eco-friendly solutions like fish-safe and oil-free turbines, enhancing environmental performance. Voith also develops pumped storage systems for grid stability and integrates digital monitoring for predictive maintenance. Voith ensures high-quality, reliable, and sustainable hydropower solutions for the evolving energy landscape. At the Cartagena shipyard, the final assembly of the S-81 Isaac Peral submarine's hull marked a significant milestone in its construction. The process began with detailed planning and preparation, followed by caulking operations to ensure watertight integrity. Skilled welders then performed high-precision welding to join the hull sections. Once complete, all parts were fully united, forming the complete resistant hull. This step symbolizes the nearing completion of Spain's first S-80+ class submarine. Shunchuan Machinery is a renowned manufacturer of high-performance lathes, offering a wide range of machines tailored for precision machining. Their manual lathes, including high-speed precision models, are built for durability and smooth operation, ideal for tool rooms and repair shops. Shunchuan's conventional lathes come in several configurations. The all-gear lathe delivers strong torque for heavy-duty cuts. The variable speed lathe allows flexible control for various materials, and the mechanical clutch lathe ensures stable performance in demanding conditions. For automated production, Shunchuan offers advanced CNC lathes. The flatbed CNC lathe provides excellent stability and is perfect for large or long workpieces, while the slant bed CNC lathe is optimized for precision, chip removal, and high-speed operation. Shunchuan combines robust engineering with modern technology to meet the evolving needs of the machining industry. The LB3000EX2 is a high-performance horizontal lathe from Okuma, engineered for precision, speed, and affordability. Built with Okuma's heat-friendly concept and rigid tilt box construction, it ensures thermal stability and accuracy even during heavy-duty cutting. The machine is equipped with a high-torque Prex spindle motor enabling both heavy and high-speed machining with ease. Its OSPP open architecture control system is intuitive, allowing seamless integration with various peripherals and making operation user-friendly. With rapid traverse speeds of 984 1181st IPM and a wide speed range of 45 to 5,000 revolutions per minute, this lathe is optimized for productivity. The LB3000EX2 supports live tooling, subspindles, and Y-axis capabilities, offering flexible configuration options. It accommodates maximum machining diameters of 16.14 inches and machining lengths up to 51.18 inches, making it suitable for a broad range of applications. Ideal for shops seeking a balance of performance and value, the LB3000EX2 delivers excellence that's accessible. The DMU600P is a high-performance, bridge-type 5-axis machining center designed for die and mold applications. It enables complete 5-sided or simultaneous 5-axis machining in a single setup, enhancing precision and productivity. As the largest in the DMU Portal series, it supports workpieces up to 40,000 kg. Equipped with a Z-axis ram and C-axis, it offers flexible head configurations. The A-axis and B-axis milling heads allow dynamic 5-axis movement, ensuring optimal surface finish and contour accuracy. Ideal for complex, large-scale parts, the DMU600P delivers exceptional rigidity, speed, and multi-face machining efficiency in one powerful platform. The VTR160A double-column machining center is engineered for powerful cutting, high precision, and multi-surface machining in one setup. In this operation, it demonstrates a full range of capabilities, from rough turning to fine finishing. It starts with a 1/2 diameter cut at 0.020 in/rev, showing excellent stability in heavy turning. Then it drills a 7/16 hole at 250 SFM with a feed of 0.012 in/rev, followed by a 1/2 - 13 tapping cycle with perfect thread alignment and clean exit. Next, it performs helical milling using a 5/8 diameter end mill, boring a hole out to 1.5, followed by a precise chamfer. A 1.5 - 10 thread mill operation cuts clean internal threads using controlled circular interpolation. To finish, it runs a 2.5 diameter feed mill at 240 IPM, removing material rapidly, and then uses a 1.5 finish mill to achieve a fine surface finish. The machine also executes a final face milling pass for high-quality surface accuracy. Additional features like cross-rail travel, automatic tool change, and quick tool setting enhance productivity, making the VTR160A ideal for large, heavy components requiring both strength and precision. The FACCIN HAV4X240 is a powerful plate rolling machine used for producing wind tower monopiles, transition pieces, jackets, and tripods. The process begins with plate feeding and alignment, ensuring correct positioning. It then performs first and second pre-bending to curve both ends of the thick steel plate. During rolling, the machine uses its variable geometry to apply strong, precise pressure, forming large cylindrical shapes. The system ensures an extremely short flat part, minimizing welding needs. Finally, the rolled plate is ejected, ready for the next production stage. This process allows for accurate forming of thick S460 steel plates, improving structural integrity and fabrication efficiency. At the Angar facility, powerful bull press machines are used for the efficient extraction of copper from electric motor stators. These robust hydraulic presses apply immense force to separate the copper windings from the steel core. The process begins by cutting or opening the stator, then positioning it beneath the press. With a single downward stroke, the bull press pushes the copper cleanly out of the stator slots, drastically reducing manual labor and recovery time. This method ensures maximum copper yield with minimal material contamination. Designed for heavy-duty recycling applications, ANGAR's bull presses are built for speed, precision, and durability, making them ideal for high-volume operations. By automating this key step in motor recycling, ANGAR supports sustainable practices and efficient raw material recovery from industrial waste. At the Challenge Aero helipad in Kyiv, Ukraine, a brand new Robinson R-66 helicopter arrives from the Robinson factory in the United States. The helicopter comes in factory-sealed crates containing the fuselage, tail boom, rotor blades, turbine, avionics, and all associated components. On day one, the engineering crew focuses solely on receiving and inspecting the shipment. Each crate is carefully unpacked, and all parts are examined for possible transport damage. The inventory is cross-checked with the factory manifest to ensure every single component has arrived intact. No assembly is performed at this stage. This day is dedicated to careful preparation. On day two, the real assembly begins. The landing gear is installed first, followed by the mounting of the turbine engine, transmission, and drive shafts. The tail boom is precisely aligned and bolted to the fuselage. Electrical systems and wiring harnesses are routed through the airframe, and the cockpit begins to take shape with the installation of flight instruments, radios, GPS, and transponder systems. As mechanical integration continues, critical balance and alignment checks are performed. On day three, the main rotor blades and tail rotor are mounted and balanced systems. The flight control system is carefully calibrated. Avionics systems are powered up and tested for full functionality. Then comes the first ignition of the turbine engine. Engine parameters are closely monitored. After successful ground tests, the helicopter performs its first test flight. It lifts off smoothly, with stable hover and responsive control. All systems read normal. The Robinson R-66 is now fully assembled, flight verified, and ready for service. Radberg operates a broad used tire collection network approved by environmental authorities, gathering scrap tires. Incoming tires are sorted and classified by size, brand, age, load, and speed rating. Specialists inspect each casing and only select recent premium casings for retreading. Every candidate tire undergoes a thorough examination. Technicians inflate the tire to roughly 30% above its nominal pressure to reveal weak spots or leaks. They then perform a detailed check of the carcass, using imaging tools to detect hidden damage in the liner, belts, or beads. Any tire showing serious defects is excluded and sent to the recycling stream. Retreading approved casings move to the remolding line. First, the old tread and any uneven sidewall rubber is buffed off the casing, yielding a smooth rubber surface. The abrasive dust is captured and reused in rubber products. A bonding layer, adhesive gum or liquid rubber, is sprayed onto the cleaned casing, and the tire is dynamically balanced on a wheel to ensure even coating. Unvulcanized tread rubber is then wrapped around the casing. The tire is placed in a heated mold, press, inflated and held under high pressure, a process akin to vulcanization, so that the new tread vulcanizes to the casing in the mold's pattern. After curing, the tire is removed and excess rubber is trimmed and buffed smooth. Tires deemed unfit for retreading go through recycling. Whole tires are fed into industrial shredders, producing coarse 50 to 100 millimeters rubber chips. The recovered rubber crumb is used in products like rubberized pavements or ground further into powder, while clean steel and fibers are recycled separately. Throughout the process, strict quality checks ensure safety. Each retreaded tire is reinflated and inspected, including a final stereograph scan. Any flawed tire is removed. The company also sells inspected used casings and rims for reuse in the industry, completing the circular workflow. Crankshaft is carefully loaded onto the massive DB 12500 grinder, aligned precisely for high-accuracy, heavy-duty crankshaft grinding. This is a river dredging project by River Machinery in Wuhan, China, featuring a custom-built amphibious excavator equipped with a cutter suction pump, a configuration that delivers both mobility and high-performance dredging capability. The operation begins with the installation of the cutter suction pump onto the boom of the amphibious excavator. Technicians carefully mount the pump head, connect the hydraulic power lines, and secure the discharge pipeline that runs from the pump to the material offloading area. The suction head is adjusted for depth and rotation, enabling it to cut into compacted riverbed sediment. Once installed and tested, the amphibious excavator enters the water. Its wide pontoons provide buoyancy and stability, allowing it to float and operate in soft or waterlogged environments where regular excavators would fail. With the cutter pump activated, the machine begins to break up dense sediment using its rotating cutter head. The loosened material is then suctioned and pumped through a high-pressure discharge line to a distant spoil site. This project demonstrates the equipment's exceptional mobility, reliability, and dredging capacity, especially in challenging terrain. By combining amphibious technology with suction dredging capability, River Machinery has created a modern, flexible solution for environmental remediation, waterway maintenance, and flood prevention projects. The Brunstable Bridge replacement project along the L4 Vorderwaldstrasse was initiated after structural assessments revealed serious deterioration in the existing bridge. To maintain traffic flow during construction, the new bridge was built on a slightly shifted alignment, just downstream of the existing structure. Construction began in September 2013, with the creation of two tall piers on steep slopes outside the Waisak riverbed. To access these difficult terrains, temporary access roads were first established along both riverbanks. Each pier required a deep foundation shaft, up to 9 meters into bedrock, stabilized with shotcrete walls and additional anchoring systems, especially on unstable slopes. These shafts were reinforced with 2 layers of rebar mesh and sprayed concrete up to 30 centimeters thick near existing foundations. Through winter 2013-2014, the piers, reaching heights of over 30 meters, were constructed using a climbing formwork system. This method allowed for rapid and precise casting of reinforced concrete in vertical segments. Prefabricated reinforcement cages were prepared at ground level and hoisted into place. With optimal site coordination, the construction team achieved a rate of 1 climbing segment every 2 days. By February 2014, all pier foundations were completed. Abutments were stabilized with tie-back anchors, each up to 29 meters long, to resist longitudinal forces imposed by the future superstructure. The next major step was installing temporary scaffolding, which presented a formidable challenge due to the steep ravine. Instead of lifting components vertically, a 900-ton scaffolding truss system was assembled horizontally at one abutment and then launched across the valley span. This advanced launching technique allowed the truss to reach its final position incrementally while handling vertical deflections of nearly 19 centimeters under load. The system supported the full weight of the bridge superstructure, formwork, and fresh concrete during construction. In July 2014, construction of the bridge superstructure began. A cast-in-place method using side-mounted formwork was used. The side spans were concreted first, followed by the central span. This stage used around 1,000 cubic meters of concrete, 150 tons of rebar, and 3,500 square meters of formwork. Once the deck was cast, post-tensioning operations followed. A total of 16 tendon bundles, each containing 12 strands, were tensioned to 230 tons each, with elongations reaching up to 75 centimeters. All tensioning was monitored with calibrated jacks and grouted afterward to ensure structural bonding. In August 2014, work on approach ramps commenced. On the Krumbach side, a 60-meter-long and 6-meter-high retaining wall was built, while the Doran side required rock cuttings, slope anchoring, and a 24-meter masonry-faced retaining wall. These earthworks stabilized the terrain and allowed for realignment of the connecting roadway. By April 2015, waterproofing of the bridge deck began. The surface was prepared with high-pressure cleaning and epoxy primer, then layered with bituminous waterproofing membranes. Curbing, drainage, and barriers followed. The pavement structure included unbound base layers topped with asphalt base and surface courses. The final 3 centimeters wearing course was laid continuously over 2 nights to ensure seamless quality and maximum grip for vehicle safety. Finally, between August and October 2015, the old bridge was dismantled. Steel beams were flame-cut, sectioned, and lifted by crane. Pier columns were demolished, and the Waisak riverbed was restored to its natural condition. The successful and timely completion of this project was made possible by seamless collaboration, expert planning, and the tireless efforts of every team involved. The road printer is a divisible paving machine of 4, 5, and 6 meters, which can pave a whole road with edge finishing at once. The machine can pave a road with a maximum width of 6 meters at once. The road width is adjustable on the machine, allowing all widths from 1 meter to 6 meters to be paved. Ideal for quick and easy road construction, it saves labor and time significantly. The Urban EM110 is a professional-grade electric wood chipper designed for processing logs and branches up to 12 centimeters in diameter. Powered by a robust 18.5 kilowatts electric motor, this chipper is suitable for demanding applications in agriculture, forestry, landscaping, municipal services, and biomass production. It delivers powerful, low-noise, and eco-friendly performance for continuous operation in both indoor and outdoor environments. The EM110 produces wood chips ranging from 7 to 22 centimeters in length, making them ideal for heating systems, composting, animal bedding, or mulch for landscaping. The output size depends on the wood type, feed speed, and internal configuration. The consistent chip size ensures compatibility with biomass boilers and chip storage systems. The chipper offers multiple output options to suit various needs. It can be fitted with a double bagging unit for mesh bags, a big bag collector, or a belt conveyor. The version featured in the video is equipped with a 2.1 meter long conveyor belt, allowing smooth and efficient discharge of wood chips directly into trailers or containers. Ideal for large-scale processing or integration into automated systems. Built with a durable steel frame and precision machined components, the EM110 is engineered for longevity, stability, and minimal maintenance. Safety features such as emergency stop buttons, protective covers, and overload protection ensure safe operation for users. Its electric motor not only reduces emissions and fuel costs, but also lowers operating noise, making it especially useful in urban or noise-sensitive areas. Quick setup, simple controls, and low maintenance needs make the Urban EM110 a cost-effective, user-friendly, and environmentally responsible solution for modern wood chipping tasks. The twist chair by Peruvian represents the perfect harmony of craftsmanship and elegant Italian design. Every part of the chair begins with solid wood, precisely shaped from carefully selected logs. The defining feature, the twisted backrest, is crafted with exceptional attention to detail. Each component of the back is individually adapted by hand to fit seamlessly with the left and right legs, ensuring symmetry and structural strength. Once the parts are dry-fitted, artisans meticulously test and adjust connections, closing even the smallest gaps. Glue is applied with care, followed by the precise tightening of all joints using high-tension clamps. This includes both the back and front assemblies, which are clamped together to hold their position during drying. This guarantees that every angle and joint remains perfectly aligned. The entire assembly process is done manually by skilled craftsmen, reflecting Peruvian's commitment to quality and longevity. The result is not just a functional piece of furniture, but a sculptural, organic form that adds sophistication to any space. The twist chair is a testament to Parada's legacy, where artisanal skill meets timeless design in every carefully joined piece. When building with foam blocks, pinobloque, accurate and even mortar application is essential for structural strength and alignment. A handmade cement mortar spreader is a simple, yet highly effective tool that helps achieve a uniform mortar layer during block masonry work. This tool is typically a rectangular metal container with an open bottom and side handles. It's designed to fit the width of the foam block. The worker fills the spreader with cement mortar and pulls it along the top surface of a laid block. As the tool moves, it evenly spreads a consistent mortar layer, reducing waste and ensuring better bonding between blocks. The handmade spreader speeds up work by eliminating the need to manually trowel the mortar for each block. It ensures clean edges, uniform thickness, and strong adhesion, which are especially important for foam blocks, as they are lightweight and require precise placement to avoid structural issues. This method is widely used on construction sites, especially for low-rise buildings, internal partition walls, and thermal insulation projects. It combines manual control with improved efficiency and better consistency. Using a handmade mortar spreader reduces material consumption, increases productivity, and enhances the overall quality of the masonry, making it a reliable tool for craftsmen working with foam or aerated concrete blocks.